Hello, this is Guillermo Campitelli, and this is the explainer for the topic Linear Models Model Comparison Approach. And we are going to see both the traditional approaches and a Bayesian approach. The topics for this explainer are the following. One, comparing two models in general. Then the second topic is maximum likelihood estimation, which is one of the traditional approaches. The third is null hypothesis significance testing, which is another traditional approach. Fourth, differences between traditional approach and Bayesian approach. And final topic is Bayes factors, which is the approach we use in the Bayesian model comparison approach. So let's start with comparing two models. And as usual, I've got questions for you. The first question is, which models did we compare in the masterclass? And the second one, why did I redescribe or reparameterized the model with one parameter? Okay, so the two models we compared in the masterclass was a model with one parameter or a simple model, and because that parameter, the best estimate of that parameter is the mean of the sample, then we call it sometimes the mean model. And a model with two parameters, which has a beta 0 and a beta 1. One corresponds to the intercept and the other one to the slope. So these are the two parameters we compared, so we went through in the masterclass. Now, why did I redescribe or reparameterized the model with one parameter? The idea is to have the same structure as the model with two parameters, and we put the constraint that the parameter beta 1 is fixed in 0. So if you fix the parameter beta 1 to 0 in using the same structure as the model with two parameters, it's equivalent to have just beta 0, because if beta 1 is 0, and beta 1, remember, that multiplies by x, so by any value of x, and that's what makes it different from the other model. But if you multiply 0 by the values of x, you will get 0. So beta 0 plus 0, it's beta 0, which is the same thing as the model with only one parameter. But why do we do that? We do that because we want to compare in some of the approaches a model, whether beta 0 is 0, whether beta 1 is 0 or is a different value than 0. So that's the reason why I reparameterized, in order to be able to do this comparison in which we have a null hypothesis of beta 1 being 0 and compared to an alternative hypothesis in which beta 1 is different than 0. So in the graph, we've got a representation of both models. In red, we've got the model with one parameter, in which the beta 0 will be around here, and this is the intercept, which corresponds to the mean of the variable y, which in this case is academic achievement, and the beta 1 is also 0. So basically the slope, there is no slope. That's why it's a straight horizontal line without any slope. Whereas in the model with two parameters, we've got beta 0, which is the intercept. So where these line intercepts in the axis with 0. So in study hours, we've got, it starts in 5, so 0 should be around here or around there. So the intercept will be around there. Okay, so, and the beta 1 is how much the academic achievement points increase as a function of 1 unit increase of beta 1. 1 unit increase of study hours. Okay, and that determines the gradient of that slope. If by 1 unit of study hours the increase in academic achievement is 0, we've got no gradient, so we've got that line. So if it is more than 0, then we've got a gradient that goes upwards. And if it is negative, then the curve goes downwards. Okay? So these were the two models that we compared. So then we explained the maximum likelihood estimation approach. Now, the maximum likelihood estimation is something that we didn't use when I explained how to do the analysis in JASP. I didn't use this approach. This approach may become handy later on in the unit. So at this stage, you just need to know what it is and how it differs from the null hypothesis significance testing approach, but you don't have to worry about how to apply these in JASP. Okay, so in the maximum likelihood method, we use the two models to predict the individual data. So instead of using a model that predicts a summary of the data, maximum likelihood predicts each of the 300 observations we have in this study. So we use the models we have about how the population is distributed. So we've got first we know about the population that, or we assume that it has a beta 1 of 0, and the beta 0 is the mean of our sample. And we assume that it has follows a normal distribution around that mean with some standard deviation. We don't know the standard deviation, but we use the standard deviation in our sample to estimate the standard deviation of the population. So based on that, on a standard a normal distribution with mean of 0, sorry, not the mean of 0, the mean of 51 in academic achievement. Then some standard deviation that we estimate with this standard deviation of our sample, we make a prediction of each of the 300 cases, observations in our study. Now, we need to calculate the probability of observing each of these observations. That's the first step. What's the probability? Well, the probability is determined by that normal distribution. So values close to 51, which is the mean, would be more likely, and values that are further away from 51 are less likely. Okay, so then we obtain the product of those values. So in the case of the model with only one parameter, then we calculate. So we've got a probability of observing observation 1 times the probability of observing observation 2 times the probability of observation 4 and 3, 4 until 300. And so the product of all these probabilities is a very low number, because remember, probabilities are numbers below 1, and so between 0 and 1. And when you start multiplying values that are below 1, you get smaller values. So that's the reason why we apply the logarithm to those values. It's just a measure for convenience. It doesn't have any meaning. Just dealing with very small numbers is uncomfortable. So if we transform values into logarithm, they become more manageable, and we can do we don't have to do multiplication, we have to do addition, but I'm not going to complicate things with that. Now, so we do that for these two stages with the two models. I explained just now how to do it with the model with one parameter. In the model with two parameters is slightly different. The assumption is that in the population, the beta 1 is the one we calculated in our sample, the B1 we calculated in our sample, and then instead of having only one normal distribution to predict all the values, we've got one normal distribution for each value of X, for each value of study hours. And the mean of those normal distributions changes for each X, and the mean will be beta 1 times X. So that allows us to have predictions that are more probable in each case. Okay, so you can see that these normal distributions, they should be a bit bigger. That's my drawing is not very good, but you can see that each normal distribution is closer to the dots. So you don't have to go very far away from the distribution to capture the dots, whereas the normal distribution, in order to capture the extremes, it's in the extreme of the distribution, so the probabilities are very, very, very low. But in these distributions, they are not so low because they are not so far away from the mean of the distribution. Okay, so but we do the same. We use the different normal distributions for each value of X, but for each of the observations, we calculate the probability of observing that value. And then we multiply as we did, and we add the logarithm in order to be more manageable. The third step is to penalize the complex model. And why we penalize? As I explained in the masterclass, we want to avoid overfitting, and overfitting is we need to avoid that, because we can have a model with more parameters and our prediction will be better, but only the prediction of these data, the data that we use to make the curve. So instead of using a line, we can use a curve with more parameters, and the prediction will be better. The more parameters we add, the more likely the better we fit the data, but only the current data. If we use a very complex model with a lot of parameters, we can even get to 300 parameters and make a perfect prediction of the data that we use to do that curve. When we want to predict the observation of data that is not in this sample, which is that what we like to do in science, we want to predict things that are beyond what the small sample that we have. When we want to do that, complex models are really bad. Why are they bad? Because they have more parameters, should be better. Well, because they are fitting the noise. So we are saying that the values we are observing here are partly determined by some process that has natural process, that some law of nature, but then part of the observations are due to randomness. And when we overfit, when we put a lot of parameters in a model, we are fitting the randomness. And the random aspect that determine one observation will not determine future observations. It will be random thing. So we cannot predict what will be in that random component in a future prediction. We know the one that just happened, the one we observe, but not the ones in the future. So that's why we have to keep the models as simple as possible. Now, that's why we penalize. And the way we penalize is using something that is called the Bayesian information criterion or a cake information criterion, but we are not going to explain that. Suffices to say that the more parameters you have, the more penalization your model will receive. And based on that, we've got two likelihoods. One likelihood for the model with one parameter, and one likelihood for the model for the other parameter with two parameters. And well, we just determine which one has the maximum likelihood. So that's why it's called the maximum likelihood method. Okay, so let's move to the second method. But before that, I ask you, now that you've seen the maximum likelihood estimation, how does it differ from the null hypothesis significance testing approach? And that's where we are going to talk about now. Okay, so that comes now comes handy the reparameterization I did of the model with one parameter. So in that reparameterization, I indicated that beta 1 equals 0. So we are assuming that there is no relationship between these two variables. In this graph, I generated random numbers from two distributions. One distribution, normal distribution with a mean of 51. That's to resemble the academic achievement variable, which had a mean of 51, and one normal distribution with a mean of 23 that resembles the study hours variable. And because I generated those numbers independently, then they are not connected. So I generated numbers. You have to assume that these are millions of numbers. They are less than millions there, of course, but assume that there is millions. This is just for illustration. And then you calculate the beta 1 there, and the beta 1 should be 0 because these numbers are not connected. They are independent, and so there mustn't be any connection. So the null hypothesis testing actually is saying beta 1 in the population is 0. So that's the first step of the null hypothesis testing approach. And then we obtain a sampling distribution of beta 1. And remember that statisticians and myself, I do it a lot, we become quite sloppy about beta 1 and the B1 in the sample. We shouldn't do that, but that's quite common. So the sampling distribution should be of B1, because that's what we obtain in the sample. Now, but technically, people use the t-test, and that's what you get in the software. When you use an analysis, you are not going to get an analysis of the last part of this process is obtaining a p-value. You will not get a p-value from the standard, the sampling distribution of the parameter. You get it from a t-distribution. And why is that? In the past, it was very important to use distributions that we know very well. Why? Because it was computationally to come up with a sampling distribution was onerous, was tremendous. But now we can do it in milliseconds with our computers. So we can actually do it. But because we follow the tradition we're still using the t-test to make the calculation of the p-value. Okay, so then the third step is to calculate the B1 in our sample, or if we are using the t-test, that's what the software does, we calculate the t-score, and the t-score is calculated with the B1 we obtain in our sample divided by the standard error of B1. So that's the standard deviation of the sampling distribution of B1s. And remember, the sampling distribution of B1s is from that population with beta 1 equals 0, we obtain a sample of 300 values, and we calculate B1. And we do that 10,000 times. And then so we have 10,000 B1s. And so with these 10,000 B1s, we've got a distribution of B1s. And that distribution has a mean. And what's the mean? We know that the mean of that distribution is 0 because it comes from a population in which beta 1 is 0. And what's the standard deviation of that distribution? Well, there is a formula to calculate that, but I'm not interested in that formula. It doesn't have any intuitive value, at least at this stage. But that is here. And that is the way we calculate the t-score, doing beta 1 divided by the standard error of B1. And then we use we compare the t-score we obtain in our sample, or the B1 we obtain in our sample, with the sampling distribution of, and t, we use the t distribution as the sampling distribution. But there is nothing that stops us to do ourselves the sampling distribution of B1 and compare the B1 we obtained with the sampling distribution of B1. And then we have to look at that sampling distribution and where our B1 or our T score stands in that distribution. If our B1 or our T score is close to the mean of those distributions, then it's probable that our score, the one we observed in our sample, comes from a population with a beta 1 equals 0. But if our score stands very far from the mean, then it's very improbable. That score is very improbable. And basically, it's very improbable that it came from a distribution with beta 1 equals 0. And if that is the case, and by the way, the p-value is what's the probability of obtaining the B1 or the T that we obtain in our sample in that sampling distribution. But it's a bit different than this. It is not the probability of observing that exact value. It is the probability of observing that value or a more extreme value. And it depends on how we define the alternative hypothesis. If the alternative hypothesis is that the beta 1 will be different than 0, then we have to look at the two tails of the distribution. So we need to see how probable is to obtain the t-score or the B1 in our sample in that sampling distribution, but actually not the exact score, but that score or more extreme. But if it is the alternative hypothesis is not directional, we have to see, let's say, if the t-score we obtain is 3, we need to look at how probable it is to obtain a t-score of 3 or more, and how probable it is to obtain a t-score of -3 or less. Okay, so that is the p-value. If our hypothesis is that the difference, the beta 1 will be higher than 0, then we only look at one extreme of the distribution. So we say how probable is to obtain the B1 we obtain, or the T we obtain in our sample, in that sampling distribution. But as I said, not just the score we obtain, but how probable is to obtain that score or a higher value. And that is the p-value. And then we use a threshold, which a popular one is 0.05. And if the p-value we obtain is less than that threshold, then we reject the null hypothesis, and we reject which in this case is that beta 1 equals 0. So that's the null hypothesis testing approach. Now, let's talk about differences between the traditional approach and the Bayesian approach, and similarities as well. And so the question is, before we go through that, try to, by yourself, identify what are differences and similarities between the traditional approach and the Bayesian approach on model comparison. Okay, so in order to identify differences and similarities, we use the Bayes theorem. And remember, the Bayes theorem has a prior probability distribution. It has what is typically called the likelihood, but I prefer to call it the probability of the data given parameter. And here is the posterior probability, and this is the probability of the data. So in terms of the probability of the data given parameter, what is typically called the likelihood, these are very similar in the traditional and the Bayesian approach. So in the traditional approach, we say, well, what's the probability of obtaining B1, which is the B1 we calculated in our sample, given that beta 1 equals 0. Okay, so that's the sampling distribution. So probability of data given parameter in the Bayes theorem corresponds to the sampling distribution. And we say that B1 is distributed normally with a mean of 0, and the standard deviation is the standard error of B1. Now, this is only applied to the null hypothesis. So that's the problem of the traditional approach. The traditional approach has a model of the null hypothesis, but no model of the null. Sorry, it has a model of the null hypothesis, but no model of the alternative hypothesis. Then we go to the Bayesian approach, and we've got that probability of B1 given beta 1, but not fixed to 0. So that is the difference. We are going to calculate this probability not for beta 1 equals 0 only, but for all the values of beta 1. Okay, so in that sense is the difference. But then the distribution we are going to use is the same. So beta 1 is normally distributed with the mean of beta 1 and the standard error of B1. So here we are going to calculate this distribution to all the values of beta 1 instead of just one value. Is this the same distribution but applied more times? And we do the same for we apply the same idea for a model of the null hypothesis and the model of the alternative hypothesis. Prior distribution. The prior distribution, we can say that the null hypothesis has a prior distribution, which is that beta 1 equals 0. And that's the same in the Bayesian approach. The only thing that, because we use in Bayesian, we use the Bayes theorem, which is a probability theorem, and then we use the language of probability, but we express the same idea. So the probability of beta 1 being 0 is infinity, so it has an infinity probability density, is to say that probability of beta 1 equals 0. And because, well, that is complemented by saying that values that are different than 0 are impossible. Probability equals 0, that means they are impossible. So we are saying exactly the same. So it's the prior for the null hypothesis in the traditional approach, and for the Bayesian approach is the same. And in the graph is represented by a spike in 0. So this spike goes towards infinity. We cannot have infinity in this graph, but that's the idea. There is a spike. All the other values are impossible. So the difference, the huge difference, is in the alternative hypothesis. The alternative hypothesis in the traditional approach is that beta 1 equals 0, is different than 0. But there is no distribution. It's just different than 0. But are the values, if beta 1 minus 100 is equally likely than minus 0.02? And what about beta 1 of 2 or beta 1 of 25? Are all the values equally likely? We don't know. That's the under definition that we have in the traditional approach. In the Bayesian approach, we provide a distribution for a prior distribution for the alternative hypothesis. And this is an important issue because the prior is the most controversial aspect of Bayesian statistics. Critics of Bayesian statistics, they criticize the use of priors. Because they say, oh, well, and the prior is subjective, so you can come up with any prior you want, and then you get the result you want because the prior influences the result you get. That's absolutely right. But what that analysis misses is that you cannot. Yes, the Bayesian approach allows you to come up with any prior you want, but you need to justify. You cannot just decide, well, I just believe this is the case, but why? I don't know. Well, if that's the case, then I would say the analysis is useless because you don't have a justification for your prior. And that's the beauty. To me, it's not the problem of the Bayesian approach. It's an advantage because we need to carefully consider the prior. Okay? Now, because of that attack of critics to the Bayesian approach, to the prior, then some Bayesian statisticians and researchers trying to develop the Bayesian approach, they came up with default priors which are uninformative. Basically, they say, okay, this prior indicates that I have no idea of what the possible parameter values in the population are, and let the data decide what to do. And that's okay. In some situations, this is the best alternative. That's the alternative that we are going to follow here when we use JASP. JASP has a default values for the priors, and I'm not going to ask you to go and change those priors, although you can do it in JASP. But we are not going to do that. We are going to use these default priors, and these are some cases. Like, for example, a normal distribution with a mean of 0 and a dispersion of 0.7 this is this distribution, which is similar to a Cauchy distribution with the parameter r 0.354. We haven't seen that distribution, and we are not going to see that distribution. Suffice it to say that it's very similar to the normal. Like this is symmetrical around 0. Or some people use the uniform from minus infinity to positive infinity. So basically that would be that all the values are equally likely. Okay, so that's about the prior. What about the probability of the observed data? The probability of the observed data for the null hypothesis, that's the value that came from the sampling distribution. So we've got a sampling distribution, assuming that beta 1 equals 0, and let's say we observe a B1 of 0.2, of 0.256. What's the probability of observing that value in the sampling distribution? I don't know, let's say 0.0005. So low probability. So that's the probability of the observed data. But remember that in the traditional approach, when we do maximum likelihood estimation, we will be interested in that value. But when we do null hypothesis testing, we are interested in the tail, so that value or more extreme. Now, for the alternative hypothesis, this is not calculated, and this is a problem to me. Now, in the Bayesian approach, for the null hypothesis, is exactly the same as the traditional approach. We assume the beta 1 is 0, and we obtain the probability of B1, the B1 we observed in our sample, and in that sampling distribution. Now, for the Bayesian approach in the alternative hypothesis, and remember, in the alternative hypothesis, we put a prior in possible values for beta 1, which gives some probability to all possible values of beta 1. And well, so then we have to estimate the probability of observing the B1 we observe in our sample for all possible values of beta 1. And so that becomes an integral, because beta 1 is not discrete. We can observe infinite numbers of possible beta 1. So when we have an infinite sample space, then we use calculus. We need to do integration rather than addition. Now we may ask why I didn't put here multiply these by the prior, because that's what we effectively have to do. I didn't put that because I'm assuming here where we use a default prior that gives equal probability to all the values. So when you have a prior that gives equal probability to all the values, in relative terms, it will not change. The final topic is the Bayes factors, and as I said in the masterclass, after you went through all the aspects of the Bayes theorem, then doing the Bayes factor becomes quite easy. So question before I go through that is, how do you calculate the Bayes factor of the model of the alternative hypothesis relative to the model of the null hypothesis, which is what I did in the masterclass. Okay, so we've got the model of the null hypothesis, we have the model of the alternative hypothesis, and those models have a probability of observing. What's the probability of observing B1 in that model? So we've got that for both models, and so here we've got what's the probability of observing B1 given H1 is true. So given the model of the alternative is true, And what's the probability of observing B1 given the model of the of the null hypothesis is true? And these two probabilities, we calculate the ratio, and that's the Bayes factor. For example, if the probability of B1 under the alternative model is 0.0032, and the probability of B1 under the model of the null hypothesis is 0.0002, then the ratio is 16, and the Bayes factor is 16, and that means that the model of, so the data under the model of the alternative hypothesis is 16 times more likely than under the model of the alternative hypothesis. And then what I said is that that's the end to me for the researcher. That's the end. That's a quantification of the evidence in favor of the model of the alternative hypothesis. We don't have to make a decision. The beauty that we don't have to make a decision is that this is a simple study in which we do one analysis. But when you conduct research, you may have a lot of variables, or you may have different conditions, and you may want to run a lot of analysis. And there is absolutely no problem because you're not making a decision. And if you're not making a decision, you're not making errors. And so by making multiple comparisons, it doesn't increase the probability of making this error because you are not making a decision, so you're not making a mistake. Now, the decisions, that's the task of other people, of politicians, administrators, authorities to whom we provide this information, and based on this information they make their decisions. And the decisions, in some circumstances, we need the evidence in favor of the alternative hypothesis should be very strong, because, for example, what we have now, it's okay. So in order to make a change, we need very strong evidence. But in some circumstances, if what we have now it's not good at all, it's really bad, then something that gives us a little bit of, even though the evidence is not so strong, then we can decide to change. So these are decisions that are not made by the researcher, they are made by the practitioners, people who will use our information to make the decisions. One important issue is that when it could be the case that the alternative hypothesis has a probability lower than that for the null hypothesis, and in this case the BF, the Bayes factor, will be lower than 1, so 0.25 in this case. It is difficult to communicate what does 0.25 mean. So in that case, what we do is to calculate the BF01, which is just inverting the numbers there, and basically this would be 4. Or we don't need to do that, we just do 1 divided by 0.25, and that's 4 as well. And so we can say now, instead of saying that the alternative hypothesis is 0.25 times as likely as the null hypothesis, we say that the null hypothesis is 4 times more likely than the alternative hypothesis. And that's it. That's the Bayes factor. It's not complicated. When you see how it's calculated with JASP, it's very, very straightforward. Is what it means. You need to go through all these steps to understand what it means. But in this, the actual calculation is straightforward when you have a software like JASP.